Okay, let's start the session. So I welcome you to the week 2 practice assignment session for the course Chemical Reaction Engineering 2. Okay, let's get into the session. You're able to see my screen?
Yeah, ma'am.
Okay, you're able to see the screen. Okay, so can we just get started?
Yeah, ma'am.
Okay, yeah, okay. So before getting on to the practice assignment, we'll have a brief recap of lectures of week 3. Okay. Uh, so do you remember, what was all covered in week 1 and week 2?
A little bit, ma'am.
So what are the things you remember? Can I just share a few points?
Um, s- 7 steps of every
Catalytic reaction.
catalytic
Okay.
reaction.
Okay. Can you just say what are those 7 steps?
One is external diffusion, internal diffusion, adsorption, reaction, desorption, and again internal diffusion and external diffusion.
Okay. Okay, that's fine. Okay. So in adsorption, again you have, dissociated adsorption and
Non-dissociative
non-dissociated
adsorption.
absorption. Yes, yes. So, do you remember what are the mechanisms, different mechanisms of absorption? Was discussed in the first 2 week lectures.
Yeah, ma'am. The mechanisms discussed like
Uh, so it was one was the single site mechanism, and then
dual site and dual. Three mechanisms were there: ma'am. Single site, dual site, and dual site dual absorption or something there.
so in dual site again you have single component adsorbed, and then dual site two components adsorbed, and then dual site, two catalysts, two components adsorbed. And then finally, you had the Ehlers-Danlos mechanism. Do you remember what happens in Ehlers-Danlos mechanism? We also discussed a question on that.
And then like a component in a gaseous phase which is near to component which occupied the site, and then they both react and form a new product.
Yes, yes. In Ehlers-Danlos mechanism, one of the components will be in gaseous phase itself, and that will react with the component that has been absorbed. Okay.
Yeah, yeah.
So these are some of the glimpses of the week 1 and week 2. And again, in the reaction limiting, it can be either adsorption limiting or surface reaction limiting or desorption limiting as well, right? And in week 2 lecture 10, design of the packed bed reactor was initiated, right? So this packed bed reactor design equation, it was continued in lecture 11. Okay. And then uh, uh, where the equation for conversion was obtained, and then uh, for the same conversion, how a design equation for a fluidized CSTR will look like was also derived and discussed. Okay.
Okay, ma'am.
Yeah. And then the lecture 12 was a case study of chemical vapor deposition method. Okay, in chemical vapor deposition also, it follows very similar mechanism to that of a catalytic reaction. Okay, where say for example, in the problem discussed, the germanium gets deposited from by reaction of germanium chloride with hydrogen. Okay, so again here a mechanism with surface reaction limiting was discussed. Okay, this was followed by lecture 13. Okay, lecture 13 was on catalyst deactivation. Okay, so the activity of the catalyst will not be the same, over years and years. Definitely there are mechanisms by which the activity of the catalyst gets reduced. uh, See, for example, in whatever, the rate equations it was developed in week 1 and 2, it was assumed that the total number of active sites in the catalyst CT, right? It is a constant. However, in reality, that is not the case. There are a lot of mechanisms by which this, the total number of active sites over the, gets reduced. Okay, that was actually discussed. So, what is the definition of a catalyst deactivation was discussed initially, and then, the type of kinetics uh, that a catalyst deactivation process follows. So, there are two types of kinetics. One is a separable kinetics. Here, the catalyst decay and the kinetics of the reaction are independent of each other. Okay, so you can separately develop the uh, equation, and then you can incorporate. Okay, for the catalytic process. Whereas there is one more type of kinetics where the the catalyst deactivation or the decay process, it is and the the kinetics of the reaction in they go hand in hand. That is a kind of past history of the catalyst process and the fresh catalyst, how it behaves. It goes hand in hand. uh, because there might be cases where this deactivation process can happen via many elementary steps. So in this case, it cannot be the kinetics cannot be separated, and it comes under the non-separable kinetics. However, for this course, only separable kinetics is discussed in detail. Okay, and then there is a the rate law was discussed. Okay, and then the catalyst decay mechanisms were all discussed. So, what do you think of activity of a catalyst? How do you define it? Do you have any thought process on how you can define activity of a catalyst?
Yeah, ma'am. It just decreases the activation energy to perform a reaction.
No, no, I'm asking. I said the catalyst has a possibility of getting deactivated. That is, the availability of sites in the catalyst will not is not a constant, but it depends on other factors as well, and it tends to change over time. So, what do you think of that activity? I'm asking.
I mean, it can be an evaporation. I mean, so that the active sites will evaporate, and if it is a liquid phase, the catalyst is um, like some.
Okay, so let me explain you the definition, the actual definition. So, activity of the catalyst is nothing but it is actually a ratio. Okay, it is a ratio of reaction rate on a certain catalyst after a certain amount of time t. For example, some time t, say for example 1 year, to the reaction rate if the fresh catalyst is used. So, it is a ratio. Okay. So obviously, fresh catalyst it will have maximum activity. That is, it's all its active sites, will be probably available, and the reaction rate that you can achieve will be maximum. But over the time, obviously the reaction rate due to some deactivation process of the catalyst, the catalyst site might not be available, so your rate will decrease. So the activity of the catalyst is nothing but the ratio of reaction rate after a certain time t to that of reaction rate if fresh catalyst is used. Okay.
Yeah.
And this catalyst decay mechanism, it happens through several mechanisms. Okay. Mhm. uh, Say for example, some of the broad classification in which catalyst decay will takes place is by sintering or aging, okay, and then fouling or coking, and then poisoning. Okay, these are some of the mechanisms. And say for example, in case of sintering, what happens is that this is basically sintering is a this process is basically a time based process. So over a long period of time, due to the exposure of the catalyst to the the reaction and to the reaction conditions, there will be some changes. For example, this change will happen through two mechanisms. So uh, in most of the cases, these noble metals like platinum and all, it is actually placed in some of the materials like you would have seen when you are writing catalyst reaction, pt slash al2o3 and all. Okay. So what happens in this case is this platinum catalyst is impregnated on the alumina surface. So this alumina will have lot of pores in which this platinum will get placed. Okay. So what happens is that due to prolonged exposure, this platinum, it starts getting agglomerated, and this agglomerate starts growing. Okay, instead of being in multiple places, okay, they all combine and form a big agglomerate. So what happens in that case, your what happens in that case is that your available active sites in the catalyst is reduced. Similarly, it can also happen by narrowing the pore size. Okay, how does the pores get narrowed? It is through blocking. Again, here again, due to long time exposure, especially to the temperatures of the reaction. Okay, most cases they are high temperature reactions. Okay, so what happens is that these metals, they tend to melt off and they try to clog the pores. So again here, your there is a loss of catalyst. Are you there?
Yeah, ma'am.
Yeah, you're
Understood,
able to
ma'am.
follow, right? So
Yeah, ma'am.
this is how a sintering mechanism happens. So one of the major ways of controlling this is by conducting the reaction at a temperature lower than 40% of the melting temperature of this noble metals, which are used as catalysts. However, in practical reasons, practical case, this might not be possible, and that is why you end up in these case of uh, you know um catalyst deactivation. Okay, so this was all discussed in the uh, lecture 13, and then lecture 14 was a continuation on catalyst deactivation, and then the decay law for a sintering process was derived and explained. And then what happens for a catalyst deactivation in case of a catalyst deactivation for an isomerization in batch reactor was discussed. The next catalyst deactivation mechanism is coking or fouling. So what do you think of this coking or fouling? What do you think of coking? What would happen to the catalyst?
No idea, ma'am.
So what do you think of coke? Don't say your Coca Cola.
No, ma'am.
Yeah, so what do you
Yeah.
think of this coke?
It's a carbon containing material.
Yeah, so it's a carbon deposit. Okay,
Yeah.
so what is happening? The carbon is getting deposited on your catalyst.
Okay, ma'am.
Okay, so that is what happens in coking or fouling. Okay, so this happens mostly in case of reactions involving hydrocarbons. Okay, uh,
Okay.
and one of the some of the mechanisms by which this can be, this deactivation can be eliminated is by using elevated hydrogen pressures, or using hydrogen rich streams. The third one is catalyst poisoning. Okay, where some of the materials, something in a feed stream, or sometimes even your reactants and products, they act as a poison to the catalyst and thus deactivating the catalyst. So the lecture 15 was on discussion of catalyst poison in the feed, catalyst poisoning by reactants and products, and then there was a discussion on various decay, a decay law. Okay. Uh, okay. So these were the contents of the week 3 lecture. Fine.
Okay, ma'am.
You're able to get some glimpse of it, right?
Yeah,
Yeah, when you go through the lectures, you will get a clear picture. Now let's go on to the practice assignment. Uh, so ethylene adsorbs on the vacant active sites of V of a transition. V is nothing but the vacant active sites of a transition metal catalyst. According to the following mechanism, you can see the mechanism. C2H4 plus 2V gives, C2H4, V and V are there. Okay. So if NT, NV and NC2H4 denote the total number of active sites, number of vacant sites, and number of C2H4 adsorbed molecules respectively, then the balance on total number of active sites is given by, what is the balance for total active sites? This is actually a GATE question in GATE 2021. Actually, when you look into the mechanism, what do you find? How is it getting adsorbed on the active site?
I mean, two vacant sites are there, ma'am, and C2H4 is getting absorbed. Does that mean that carbon is absorbing at one vacant site and hydrogens are absorbing on another vacant site, ma'am?
Uh, can you just say it in a much more precise form? What kind of mechanism actually it is happening? It is more of a dissociative adsorption, right?
Yeah, ma'am.
We don't know how it is, and the the image doesn't show how it is actually getting dissociated, but it is some dissociative mechanism because this C2H4 is getting adsorbed on two active sites.
Yeah, ma'am.
So now tell me, what will be the balance equation for total number of active sites? So will it be Nt equal to Nv plus Nc2H4, or will it be Nt equal to Nv plus 2 times of Nc2H4, or Nt will be 2 times of Nv plus Nc2H4, or will it be Nt equal to Nv plus 0.5 Nc2H4? What will be the balance equation?
And third option, ma'am, Nt equal to 2 NV. Two number of active sites are vacant sites are there, and one number of C2H4 C2H4 is there.
Is it C? Is it C?
Mm, I'm thinking of.
I'm not saying you are right or wrong, but I'm just asking you again to give a confirmed answer.
Ma'am, it's option one, ma'am.
Is it option 1?
Yes, ma'am.
Okay, so shall we see the answer?
Yeah.
It's actually option B, because NT is total active sites. Okay, NV is a free active sites, and NC2H4 is the active sites occupied by
C to H4.
ethylene. Ethylene, right? C2H4. That means if you just look into this reaction, you could say that, this ethylene is occupying two active sites, right? So number of active sites occupied by ethylene will be 2, right?
Yeah, ma'am.
A single ethylene will occupy two active sites, right? So it should be 2 in 2 into number of active sites occupied by ethylene, right?
Yes, ma'am.
So it is Nt is equal to Nv plus 2 Nc2H4. Okay, don't forget this. This is the basic, balance, right? You
Okay, ma'am.
shouldn't get, this should, seeing this 2V, you shouldn't think of it as 2NV. It should, give you a, idea that this C2H4 is going to occupy two sites.
Okay,
Okay,
ma'am.
it's okay. Now let's go on to question number 2. In catalyst poisoning, the poison deactivates the catalyst by, how do you think it would deactivate?
Ma'am, your screen is not being shared, ma'am.
Oh, is it not shared?
I mean, second question is only visible.
Oh,
Okay,
wait.
okay, ma'am. Now it's visible.
Wait. Now
Yeah, ma'am, it's visible.
it's visible. Okay. In catalyst poisoning, the poison deactivates the catalyst by, what is the mechanism you think it would deactivate the catalyst? You have any clue? I told on sintering. I told on, cooking.
Cooking and
But
okay.
poisoning, I didn't, explain in detail when I was discussing the brief
Yeah, ma'am.
summary.
You just said about poisonous.
So, because I know that I am going to ask a question on that.
Okay, ma'am.
So, you have any thoughts how it might deactivate the catalyst? So, shall I tell the answer?
Dividing it. I mean, breaking the catalyst.
No. So, what it does is that it, gets absorbed through chemisorption. Okay, on the catalyst side, irreversibly it gets absorbed through some chemical absorption mechanism. So what this poison, so this poison can be some, uh, a different material completely, which is coming from the feed, because in most of the cases, the feed might not be a very pure, components. Like for example, in the previous case, it cannot be, it might not be, pure ethylene. So it might be a combination of ethylene and propylene. There will be some quantity of propylene. So what this propylene might do, for, say for example, in the previous case, is that this propylene might have, kind of a strong adsorption with that of the catalyst surface, and it will form a kind of strong, it gets strongly adsorbed to the catalyst surface. So once propylene gets adsorbed, the main reactant is ethylene, correct? So this ethylene doesn't have that particular site for it to occupy and get converted into product, right? So this is
Yeah.
one mechanism in which some other component or some other impurity in the feed will cause poisoning. But there are also cases where either the reactant or the product acts as a poison. So what happens in this case is that in this case also, no, the reactant, it gets strongly adsorbed, irreversibly adsorbed on the catalyst side, okay, and doesn't get converted into product. Or otherwise, the product formed, it will get strongly adsorbed, and you know it doesn't allow the reactant to take up that active site, so that active sites become unavailable. So this is how a poisoning mechanism take place. Okay.
Okay, ma'am.
Yeah. Okay, now let's get on to question number 3. Titanium dioxide is a wide band gap semiconductor that is showing promise as an insulating dielectric in VLSI capacitors and for use in solar cells. Is there anyone? Jnaneshwar. Okay, welcome Jnaneshwar. So we started discussing on the uh, practice assignment. Okay.
Okay, ma'am.
Okay. So did you go through the lectures?
Yes, ma'am.
Okay. So what was the lecture on this week 3 content I'm asking on?
Catalyst deactivation.
Yes. Yes. Correct. So we were discussing, some problems. Okay. We are into the third problem. Okay. So
Okay, ma'am.
let's get on to the third problem. Okay, so titanium dioxide is a wide bandgap semiconductor that is showing promise as an insulating dielectric in VLSI capacitors and for using solar cells. Thin films of titanium dioxides are to be prepared by chemical vapor deposition from gaseous titanium tetraisopropoxide. Okay, the overall reaction is given by, so the titanium the titanium tetraisopropoxide, it gives titanium dioxide plus C3H6 plus water. Okay, this reaction mechanism in a CVD reactor is believed to be it's a CVD mechanism, CVD, chemical vapor deposition mechanism by which this reaction take place. So the reaction mechanism is as follows. What happens is that this TTIP, two molecules of TTIP will form some intermediate plus one set of reaction products. So this reaction products can be water and C3H6. Okay, and then this intermediate that forms, it gets adsorbed on the active site of the catalyst, okay, and form I dot S, and this I dot S intermediate, which is adsorbed on the active site, it gets converted to it helps in deposition of formation of this titanium dioxide that gets deposited, plus another product is formed which is P2. Okay, now assuming the homogeneous gas phase reaction of TTIP is in equilibrium, okay, that is this first reaction, two molecules of TTIP giving a intermediate and P1, that is a equilibrium reaction. Okay, now derive a rate law for deposition of titanium dioxide. Okay, the experimental results show that at 200 degrees the reaction is second order at low partial pressures of TTIP and zero order at high partial pressures of TTIP, while at 300 degrees the reaction is second order in TTIP over the entire pressure range. Now discuss these results in the light of rate law you derived. Okay, now we have to derive the rate law. Right? You're able to get some insights. Now let's solve this problem. Okay, I think one of you had gone through the lectures, right?
Yes, ma'am.
So can you say how to start with this? We have the reaction, this TTIP gives titanium dioxide plus 4C3H6 plus 2H2O. That is the overall reaction. And the gas phase reaction, which is in equilibrium TTIP, two molecules of TTIP will give intermediate plus P1. And then this intermediate plus S, that is, it gets absorbed on the active site. And once it gets absorbed on the active sites, it deposits this TiO2, and then one more product P2 is formed. So how to start with this problem?
First, we have to write absorption reactions, man.
Okay.
Adsorption reactions, we have to write first absorption reactions, man.
Okay, what is the adsorption reaction?
Adsorption reactions, I think. Yeah.
Which is the adsorption reaction here?
I
I
plus S
plus
is
S,
I.
plus IS.
Yes, yes, okay. So now let's get started on how to solve this problem. So now we'll start with rate of deposition of TiO2. Okay. Uh, it is given by, what is the rate of deposition of TiO2 from the reaction? So it's which equation you have to use for rate of deposition of TiO2.
Last equation.
Yes. So your rate of deposition is given by Ks into FIS. So Ks is a reaction rate constant, right? So what is FIS? What is FIS?
Fractional concentration of I and the AS, man.
Yes, yes. So it is the fractional, concentration of,
IS, man.
IS. That is, I that is adsorbed on the uh, catalyst surface. Okay. Now, how do you write the mass balance for the catalyst site? So, yeah, FIS is nothing but your fraction of site occupied by this intermediate I. So, how do you write the mass balance for the catalyst site? There are some sites occupied. So, there will be some other sites that are vacant, right? So, your mass balance for catalyst site will look like this. So, it is the fraction of vacant site plus fraction of site occupied by the intermediate I is equal to 1. Why is it 1 instead of FT?
It's in fraction, man.
Yes, perfect.
The total
Since it
fraction
is
is
in
1.
fraction, so the total will be 1 since it's a balance equation. Okay. So from this, uh, so you just keep that aside. Now let's look at rate of adsorption of I on the catalyst site. So how do you write the equation for that? A rate of adsorption of on catalyst site. So this I plus S gives I dot S. How do you write the equation?
Ka into F of V into F P partial pressure of I, man.
Okay. Is it only that?
partial pressure of I
minus Ks
minus
into FIS.
So it'll look like this. So your rate of adsorption of I is, since it is a reversible reaction, so you have to write this Ki into, as you said, it's partial pressure of I into, fraction of vacant site minus fraction of site occupied by I divided by the equilibrium constant of I, the equilibrium adsorption constant of I. Because you are writing this K, small ki, the forward reaction constant, outside, you are just, dividing it by the equilibrium rate constant in the denominator. Fine. Now, from this, so now let us assume this process where the rate of deposition is going to be the rate limiting step. Okay, so then what happens?
absorption is equal to 0 ma'am, at equilibrium conditions.
Yes. So, assuming surface reaction as rate limiting, therefore, this adsorption rate equation is approximately equal to 0. So, from this, what you will get? Fraction of IS, right? Fraction of active site occupied by I is equal to Ki into partial pressure of I into Fv, right?
Yes ma'am.
Yes. Now, how do you proceed? Now, we have to
Now
substitute
we will
is Fis in the mass balance equation, and you will get, what is Fv. Correct? It'll be Fv is equal to 1 by 1 plus K1 and into P, partial pressure of I. Correct? Now,
yes ma'am.
the next step, we have to, uh, you know, uh, uh, substitute in the deposition rate equation. So rate of deposition is Ks into FIS. So in this, you will replace FIS by, substituting what will be Fe and what is the, expression you got for FIS from the adsorption equilibrium, equation. Okay, and then you will end up with this rate of deposition is Ks into K1, sorry, Ki into partial pressure of I by 1 plus Ki into partial pressure of I. Okay, now say me, is this equation sufficient to find the rate of deposition? Do you have all the, required information, or this equation further needs some modification?
You can take K as common and cancel it.
Okay, once, uh, okay, so once you take, oh, how can you take K as common? It's already this one.
AI.
No, again you will end up in some of the, modified form of the same expression only. I'm asking you, so if this is the rate equation. Okay, so will you have all the, measurable parameter data in this equation? Or I'll put you in, I'll put it in a different format. So, or all the parameters measurable, either through some uh, thermodynamics or some, databases, uh, and through experiments you can get all the, parameters that are mentioned in this, all the terms that are mentioned in this expression. Because your equilibrium constants, reaction rate constants and all, you'll get from some standard tables or from thermodynamics and all. Okay, so will you be able to measure the partial pressure of I, of component I, in this in this expression through experimental
No, ma'am.
technique? Will you be able to measure?
ma'am.
Huh?
It is not measurable quantity.
Yes. Yes. Why is it not measurable?
On dissociation reaction, ma'am. So we have to further manipulations basing. We have to do further manipulation basing on dissociation reaction.
Is it that way? It is because it is an intermediate, right? So it gets converted, and you might not know whether you can get it in the exit stream or not and all, right? It is an
Yes, ma'am.
intermediate in the reaction, right? This is the reaction sequence. So this is neither in the inlet stream, not in the outlet stream also. So this is some intermediate. So in most of the cases, this intermediates, identifying the concentration of the estimating the concentration of intermediates is difficult. So obviously you have to convert it into some other format so that you will get all the measurable parameters in the rate expression. Okay, that is what, since I is an intermediate, partial pressure of I is not a measurable quantity. So in order to replace you know the partial pressure of I with measurable quantities, what should we use? I'll just go back to the set of reaction mechanism. So what can be used to convert this non-measurable partial pressure I to some other measurable parameter? Which one should we use?
Second reaction.
Hmm?
TTIP plus TTIP gives rise to I plus G.
Yes, yes, it is the gas phase reaction where the TTIP gets converted to this intermediate, and P1 can be used for converting this non-measurable quantity of Pi to measurable quantities of P1 and TTIP, P of TTIP. Okay. So now one more information they have given in the question, how you can actually measure that. What is that information? Can we just look through the question? So they have given us this point. Assuming the homogeneous gas phase reaction for TTIP is in equilibrium. Okay, we have to use this information and then derive an expression. Okay. So, this reaction TTIP, two molecules of TTIP reacts to form I and P1 is a gas phase equilibrium reaction. And let us consider the equilibrium constant for this reaction is Kp. So from this, you can find out the expression for what is the expression for Kp. Correct? So
Yes,
Kp is
ma'am.
nothing but your partial pressure of your products to partial pressure of reactants, right?
Yes, ma'am.
Yes. So Kp is partial pressure of I into partial pressure of P1 by partial pressure of TTIP the whole square. Correct? Now, once you rearrange this expression, you will get to find what is the expression for partial pressure of I. So we get into this expression for partial pressure of I. Now we have to substitute this expression into the rate of deposition of TiO2 expression, right? So once you substitute the partial pressure of I in terms of partial pressure of TTIP and partial pressure of P1, you will get you will end up with this kind of an expression. Okay. So this is kind of the second expression is a simplified form where I have taken all constants in the numerator together as k, and similarly small k, and all the constants in the denominator, that is ki and kp, as a uh, as capital K. Okay. Now we have two more questions. So they have asked first in case 1 at 200 degrees at low partial pressure of TTIP. What is the case? They have asked it follows a second order in terms of TTIP partial pressure. So how is it possible? How do you convert this expression of rate of deposition of TiO2 to a second order expression in terms of partial pressure of TTIP? The information given is that at low partial pressure of TTIP. So what happens to this expression? What modification you can make to this expression so that it,
Partial pair of TTIP set to 0, man.
if I set to 0, uh, will you get a second order expression?
It will become a 0, man.
So how do I take this
Ma'am,
expression?
we think that partial pressure of product one is uh, so much higher, ma'am. So
Can
that
you? I think there is a disturbance in your voice. Uh,
the denominator will become
Rahil, can you just type in because your
1 plus 0, ma'am.
voice is intermittent. Can you just type in what you want to say, or just can you just try saying it again? Are you typing, Rahil? Are you typing anything? Mm, okay. Anyway, we'll just proceed with this. We shouldn't completely take the partial pressure of TTIP to be 0.
Hello, ma'am.
Yeah. Yeah, tell me, Rahil. You were trying to say something. I think you're on mute again. Hello. Okay, you're saying assuming partial pressure of P1 is high. It is not the case. Actually, how you have to consider is that so you have this expression rate of deposition is equal to some constant K into square of partial pressure of TTIP by partial pressure of P1 by divided by 1 plus K into partial pressure of square of partial pressure of TTIP by partial pressure of P1. Now what you have to do is that they have given at low partial pressure of TTIP. That means, so this is you have to look into the denominator of the expression. So when you look into the denominator of the expression, when you have very low values of this partial pressure of TTIP, then this whole second term of this expression becomes very small compared to 1. Right? Correct? Hello? Are you both there?
Yes, man.
Yeah. So this becomes very small. So what you can do is that you can just eliminate this term in the denominator alone. Okay, that is what. So your K into partial pressure square of TTIP, because here already your partial pressure is very low and the square, say for example, the partial pressure is kind of zero point 0.2, right? When you square it, it becomes 0.04, right? So it becomes very small. Correct? So what happens is that this second term becomes very small compared to this first term in the denominator. So since it is very small compared to the 1, so you can eliminate that term. So you will end up with rate of deposition is a second order expression with respect to partial pressure of TTIP. Okay. Now case 2. At high partial pressure of TTIP, what will be the case? Will it become zero order? How will it become zero order? Because they have given that at high partial pressure, it will become zero order. So how does it become zero order? Any thoughts or shall I just proceed? Can any of you reply? Shall I just proceed with how to go about this?
Okay, ma'am.
Okay. So here again, you have to play with the denominator only. So in the second case, they say that the partial pressure of TTIP is high. So if it is high, again if you look into the denominator term, there is a square of partial pressure of TTIP term. Correct? So when the value is very high, then what happens? This second term in the denominator expression becomes very much higher than the first term. Correct? So what you do is that you will eliminate the first term, that is 1 you will eliminate, and you will get an expression K into partial pressure square of TTIP by partial pressure of P1 divided by again capital K into partial pressure of TTIP by partial pressure of P1. So you can just cancel both these terms. Correct? And you will end up with some constant. So small k by capital K. So that is nothing but your rate of deposition is independent of the partial pressure terms of any of the components in the system. That means it becomes a zero order. Fine. You are able to understand?
Yes, ma'am.
Yeah, okay. Now let us go into the case 2, where at 300 degrees centigrade, they have said that the expression for any partial pressure of TTIP, it becomes second order. How can you derive such a case based on the rate expression derived? Sorry. So for this case, what happens is that for an exothermic adsorption process, as the temperature increases, the adsorption equilibrium constant decreases. Okay. So you have this expression. You have this reaction. I gets adsorbed on the active site as IS. Okay. So now you have the rate of deposition expression as this. Right. So in this case, what happens is that this Ki is the adsorption equilibrium constant of I. So at high temperatures, so 300 degrees is higher than 200 obviously. So at higher temperatures, what happens is that this Ki term, becomes very small. Here again, in the denominator expression, when Ki is very small, then this second term can be eliminated. So you will end up with an expression where the rate of deposition is second order with respect to partial pressure of TTIP. Okay, that is why at higher temperatures, in the entire partial pressure range of TTIP, the expression is second order with respect to TTIP. Okay, hope you all got it. Right? You are able to understand, right?
Yes, ma'am.
Okay. Okay. Now let's go on to next question. So catalytic dehydration of methanol to form dimethyl ether and water was carried out over an ion exchange catalyst. The packed bed was initially filled with nitrogen and then at time t equal to 0, the N2 in feed is switched to pure methanol vapor entering the reactor at 413 Kelvin, 100 kilopascal and 0.2 centimeter cube per second. Okay, this is the volumetric flow rate of methanol vapor that is entering with a partial pressure of 100 kilopascal at 413 Kelvin once, at time t equal to 0. The following partial pressures were recorded at the exit to the differential reactor containing 1 gram of catalyst in 4.5 centimeter cube of the reactor volume. Okay, so this methanol dehydration reaction, it is carried out in a packed bed reactor. This packed bed reactor is having a certain volume, and it is also having certain weight of catalyst that is been placed in this reactor. Okay, and the reaction is as follows. So 2 moles of methanol will react to give 1 DME, that is dimethyl ether, plus water. Okay, so initially this reactor was filled with nitrogen, but at the start, at time t equal to 0, this nitrogen was replaced by methanol. Okay, and you have time based data for partial pressure of different components: nitrogen, methanol, water and DME. Okay, at the exit of the reactor, that is at this point. Okay, you are able to get it right? You are able to understand the question, right? Because when you see the data, you will see that uh, you know uh, the partial pressure of nitrogen is at 0 is 100, and then at 10 is 50. At 50 seconds it is 10. So one may think, why is nitrogen still coming when they say that at time t equal to 0, nitrogen in the feed is switched to pure methanol, right? You would have had that doubt, right, when you looked into the data. Hello, are you both there? Yeah, okay. So this is because, though at t equal to 0 methanol is fed, still, there will be some nitrogen within the reactor which will, come out at a particular rate from the reactor. Okay, that is why, you still find nitrogen in the exit of the reactor. Okay, till 100 seconds. In 150th second only, there is no nitrogen found. Till then there is some amount of nitrogen in the reactor as well. Okay, now they have asked you to derive a rate law for the above. So how do you, derive the rate law for the above? What is the scheme you will follow? They've given some data and some information as well, right? So they've given some data and information as well. So how do we arrive at the rate expression? Any clue how to start, solving this question? Or no? Okay, Rahil is message no in the chat box. Okay, okay. Now we'll solve this question. So they've given some data, right? And we have been given some information also. The temperature is at 413 Kelvin, and then the inlet partial pressure of methanol is 100 kilopascal, and then weight of catalyst is 1 gram, and volume of the reactor is 4.5 centimeter cube. So now with this information given of time-based data for partial pressure of the components from the reactor, exit of the reactor, you can plot some graph, right? So that is what I have done. So this is, you know, the exit partial pressure of different components versus time. So what does this say? What kind of observations you get to see from this graph? What is the information you get to see from this graph? You can just see this graph and say what are the observations. What happens to the partial pressure of nitrogen? What happens to methanol? What happens to dimethyl ether? And what happens to water? What is it you could observe for each case? So your blue curve represents nitrogen partial pressure, and then your orange represents methanol partial pressure, and then your gray represents water partial pressure, and finally uh, your the yellow color represents the dimethyl ether partial pressure. So what is it you could observe? What is the trend you could observe for each of these? After some time, reactants will come to stable partial pressure. That is what you're saying. Can you just say me for each of the case? And why does it happen in each of the case?
Because a reaction occurs, ma'am.
A reaction occurs. So what is it happening? What is happening? What is the trend of the graph you could observe for each? So for nitrogen, it is decreasing.
It
Why?
decreases, ma'am.
Why?
And
Because yeah. Tell me.
it got reacted, ma'am.
Did it get
And
reacted?
then
Did it
uh,
get reacted?
cat- it's a catalyst, ma'am. Yeah.
No, it is not a catalyst. It was just initially there. Okay.
Okay. Then how does its pressure decrease, ma'am?
How and why? Why? Because what happens at time t equal to 0? At time equal to 0, your nitrogen is completely replaced by methanol in the inlet, right? So
Yeah,
there
ma'am.
is no more nitrogen that is being given to the reactor, right? Whereas whatever nitrogen was inside the reactor has to come out, and it is taking some time to completely come out. That is why it is not going to zero at the exit of the reactor immediately, but it is taking some kind of 100 seconds or 150 seconds to come out completely, and that is the reason why nitrogen is decreasing. And then what do you see in the case of methanol at the exit?
Its pressure increased, ma'am. Partial pressure.
Is it only increasing?
Yeah, ma'am. Increasing and got constant.
Yes. So it is increasing and then it is getting constant. Okay. So initially, why is it increasing and then getting constant?
Up to its capacity, the pressure of it increased, and then it's done with the pressure, ma'am, and it got a constant.
So what is happening in this case is that methanol is the main reactant, right? So uh, initially once you feed, it has to pass through the reactor, get reacted, and there will be some unreacted methanol also. So which is coming out. Initially very small quantity is coming out. Later it gets to a constant value due to some reaction, due to some amount of conversion. Okay. Now, next you have to observe two things. One is about the dimethyl ether. When you look into dimethyl ether curve, you could find that it initially increases and then starts decreasing. Right? Why is it happening? And also, you could observe one more, that water is one of the products that is formed. The concentration initially increases and then gets to a constant value. Why is it happening? Do you have any thought?
No, ma'am.
Okay. So as I said, at exit, the partial pressure of nitrogen decreases with time. Methanol, it increases and then becomes constant. Water increases and then become constant. And then DME, it increases and then decreases, and then over a point of time, it becomes constant. So, what is the implication, or, how do you really, interpret this information and then get to a rate law? We'll just see in that. So, it can be observed that rate of formation of DME is higher initially. That is why, till 60 seconds, still 50 seconds, you could see a rapid increase, right, in DME concentration in the exit. Whereas in the later stage, what happens? It decreases and then comes to some constant value. So why is it happening is that one of the probable reason might be, or we can propose to form a rate law, is that water, which is one of the products, okay, what it might probably do is that it might not get initially absorbed on the site, but as the time proceeds, once more reaction happens and more water is obtained, the concentration of water, it reaches a constant value, which might be possibly due to the fact that the water is getting absorbed on the sites. Okay, so water starts getting absorbed. So that is the reason the the dimethyl ether concentration in the exit of the reactor, it starts decreasing and then over a period of time it becomes constant. Right?
Ma'am, can you please explain again, ma'am?
See, now what happens is that initially, if you look into uh, the dimethyl ether curve, it increases rapidly. Why? Because you know uh, what can be the possible process is that the reaction, you saw the reaction here. In the reaction, two molecules of methanol will react to form DME and water, right? So this DME and water starts coming out once it is formed. But when you actually look into the exit concentrations, initially till 50 seconds the DME is coming out, a lot of DME is coming out. Whereas after that, the product formation, I mean the concentration of DME that is coming out is reduced. That means there is some hindrance to the reaction, right? Something is happening that the reaction is not, the conversion is not happening to that extent, correct?
Yeah, ma'am.
Yeah. What is that? So that might be possibly due to the adsorption of water on the active sites. Why do we say that? Is that when we look into the exit concentration of water, it initially increases and then it becomes kind of a stable value. So that means if once it has to get stabilized, there might be some possible mechanism by which it is getting adsorbed on the surface of the uh, active site. So when water is adsorbed, so that particular active site is not available for the methanol to react to form more product, and that is why there is initially a dip in the conversion to DME, or the partial pressure of DME, or in the concentration of DME, which is which you get. You are able to understand now?
Yeah, ma'am. Completely understood, ma'am.
Yeah, fine. So that is what is happening. Now we have to propose a mechanism for this. So what is the mechanism that can be proposed? So based on this probable mechanism that was discussed, so the rate law can be as follows. So the probable mechanism of reaction can be as follows. So this methanol, so obviously it is a catalytic reaction. So this methanol should get adsorbed to the active site for the reaction to happen, right? So that will be the first step. So this gets adsorbed reversibly to form, uh, you know, uh, uh, methanol gets adsorbed on the active site. The second step, so 2-methanol will form DME plus water that is adsorbed on the active site plus one free active site, because here since you have this stoichiometric equation with two molecules of methanol reacting, so there will be two active sites. So 2-methanol and active sites will react. So obviously, in one of the active sites water is getting adsorbed and the other active site is free. This is the step 2. Fine. And this one more thing you can observe is that this is a irreversible mechanism, which is what we are proposing. Keep that in mind. And then again what happens, this water gets desorbed to form free water and then a free active site as well. Okay, this is going to be the proposed mechanism. Now we have to write the rate law expression, right? So now how to start with the rate law expression? So as usual, we can assume that the surface reaction is controlling. Okay. Now in the next step, since the surface reaction is irreversible reaction, then a pseudo steady state for intermediates is assumed. Do you remember in the first 2 weeks lecture, in one of the lectures there was a discussion on the pseudo steady state, where one or more of the reaction mechanisms is irreversible, right? In that case, we assume a pseudo steady state for the intermediates. So what does that pseudo steady state for intermediates mean? This was explained in I think week 1 or week 2 lecture, pseudo steady state for intermediates. Do you remember?
No, ma'am.
Okay. So in case of pseudo steady states for intermediates, so this assumption is basically made when one or more of the reaction schemes is irreversible. Okay, in the mechanisms proposed. So here you could see that the surface reaction mechanism is irreversible. So you could assume a pseudo steady state for the intermediates. So what does the pseudo steady state means is that the rate of formation of the intermediates is equal to 0. So here we have two intermediates. One is methanol that is the adsorbed methanol, the reaction of adsorbed methanol on the adsorption of methanol on the surface, and then the reaction of adsorption of water on the surface. So these two reactions are assumed to be equal to, rate of reactions are assumed to be equal to 0. Okay. Now, so based on this, what we can write? So first, methanol, it is getting adsorbed. So this reaction, you can again write the rate expression. Correct. So this reaction is, you get the rate expression as km, forward rate constant of methanol, multiplied by partial pressure of methanol into free side, minus your concentration of methanol that is adsorbed on free sides by the equilibrium rate constant of the methanol adsorption, right? Since this intermediate formation reaction rate is equal to 0, you will get an expression for concentration of the methanol that is adsorbed on the catalyst surface. Similarly, you will also get an expression, very similar expression, okay, for water that is, concentration of water that is adsorbed on the active surface. Okay. Now, the rate expression for the reaction is as follows. So, since it is an irreversible reaction, so your rate expression RS is Ks into concentration of adsorbed methanol. Sorry, it is actually Me dot S. Okay, there is a typo error. Concentration of the adsorbed methanol square, because the stoichiometric coefficient is 2, right?
Yes, ma'am.
Yeah. Now we write the balance for the free sites. Sorry, total number of active sites, and then substitute the expressions for your intermediate concentrations, and then you will get what is the expression for the vacant site. So substituting that, you will get into expression for the reaction rate, right? This is what is the expression for the reaction rate. So where you get your reaction rate is some constant into reaction constant into square of your methanol partial pressure square of methanol partial pressure divided by 1 plus equilibrium constant of methanol into partial pressure of methanol plus equilibrium constant of water into partial pressure of water, the whole square, right? You are able to understand that, right?
Yeah, ma'am.
Sorry. Now,
Ma'am, can you please go back, ma'am, so that I can take screenshots?
don't worry, this will get uploaded. Your
Oh, okay.
the live session will get uploaded.
Okay, ma'am.
Okay. Anyway, if you want, you can just take a screenshot, but still it will get uploaded. Okay. Now let's go on to the final question for this session. So, elementary irreversible gas phase catalytic reaction A gives B with some rate constant K1 is carried out isothermally in a batch reactor. The catalyst deactivation. One more thing. You saw this mechanism, right? This stream of mechanism where you saw water getting absorbed is affecting the conversion, right? So is there a possibility of poisoning in this scheme of reaction?
Yes, ma'am. Water is just um, not allowing more methanol to react with active sites, ma'am.
Yeah, here it is actually exactly not completely a poisoning, but if this water, if it gets irreversibly absorbed, then it becomes a poisoning process. Okay, so this is a poisoning process where your product acts as a poison to the catalyst active site, right?
Yeah, ma'am.
Yes, you have to try to correlate when you find something of similar mechanism. So when if this gets irreversibly absorbed at some particular concentration, then this this water becomes a catalyst poison, and this is a catalyst poisoning due to one of the species of the product stream. Okay. Yeah. Now, let's get on to the final question for this session. So elementary irreversible gas phase catalytic reaction, so A gives B, okay, with some reaction rate constant K1 is isothermally carried out in a batch reactor. The catalyst deactivation follows a first order decay independent of concentrations of A and B. Determine the general rate expression for catalyst activity as a function of time. Make a qualitative sketch of the catalyst activity as a function of time. Write a general algorithm and derive an expression for conversion. for this scheme of reaction in a batch reactor. So how to start about this? So determine the general rate expression for catalyst activity. So how do you determine? With what information you will determine the catalyst activity? And do you have any information with which you can derive a rate expression for catalyst activity? Just go through the question and say. Sorry. Or shall I start solving the problem?
You may start, ma'am. I'm not getting anything.
Okay. Okay. So to derive at the rate expression for catalyst activity, you have been given the information that the catalyst deactivation follows a first order decay, which is also independent of concentrations of A and B. So that means this catalyst activity decay, the catalyst decay is independent of concentration of A and B. So CA and CB are not going to affect your catalyst activity decay. And also they have given it as a first order decay. So first order decay means, first order reaction means, how do you write the expression for a first order reaction? A normal reaction.
R equal to KCA, ma'am. Or KCA, any contract.
Yeah, R is equal to KCA. Now here, what is the differential form you will express it as?
KCA by DT. K,
dCA by dt is equal to
R equal to K into DCA by DT.
K into dCA by dt. No, somewhere you're missing. Your R is nothing but, your reaction rate is nothing but, is
K.
equal to dCA by dt, which is equal to K
K.
into Ca, right? That
Yeah,
is
ma'am.
how you write the expression for first order reaction, right?
Yeah.
Yes. So here also it is very similar. So here it is nothing but your catalyst deactivation. So instead of your Ca, you write A, which is nothing but your catalyst activity. So dA by dt is equal to Kd into A. Now, how do you get an expression for A from this? Rate expression for activity. You have dA by dt is equal to Kd into A, where Kd is your decay constant.
A equal to 1 by KD into dA by dt. No?
Is it so? First, you have to integrate this expression. So, integrating the above equation, you will get an expression for A of t. That is, activity as a function of time is nothing but, once you integrate, it is just your mathematics. So, dA by A, integration of dA by A is equal to Kd into integration of t. So, you will get the expression as A of t is nothing but exponential of minus Kd into t. Right? This is what is the expression. That means there is an exponential decay. So how does this curve look? Because the second part of the question is make a qualitative sketch of the catalyst activity as a function of time. How does this curve look? Can you try drawing that curve and show? The expression shows that it is an exponential decay, right? Can you draw and show through your video? Or shall I show?
Show itself, ma'am.
Huh? You want to try?
No, no, ma'am. You show.
So your exponential decay is nothing but, so initially your activity will be 1. right? A fresh catalyst activity will be 1. So it is having an exponential decay with time. So this is how the curve looks. The exponential curve, decay curve, right?
Okay, ma'am.
Yeah, okay. Now we have to write a general algorithm and derive the expression for conversion in the case of a isothermal batch reactor. Okay. Now, what are the, how do you do it? They've given batch reactor, right? So, you have to write the performance equation of a batch reactor. So, batch reactor in which catalytic reaction is taking place, right?
Ma'am.
Yeah. So, your batch reactor, performance equation is Na naught into dx by dt is equal to minus Ra prime into W, where W is the weight of the catalyst. Okay. Now, rearranging this expression, you get dx by dt is equal to minus Ra prime W by Na naught. So,
Ma'am,
for
what is W, ma'am?
weight of the catalyst.
Okay.
Because this is a catalytic reaction, right?
Okay, ma'am.
Yeah. So, and then phrase this Na naught in terms of your concentration. So, Ca naught is equal to Na naught by V naught. What is V naught? V naught is nothing but your
Reactor, ma'am.
volume of the reactor. Yes.
Ma'am,
Yeah.
why did you indicated that RA as R dash A?
That is the expression in terms when you have different expressions when you express this rate law with respect to a catalytic reaction, with respect to a solid phase reaction, with respect to a volume of a reactor, right? You will write it as minus Ra when it is the volume, total volume, and then volume of the reactor. You will write. I think you could recollect it from your CRE1 from 11th scale. You will write three different forms where you will use for surface reaction with the surface term involved. Then it will be like minus Ra double prime, right? And then with the volume of the reactor, I think it's minus Ra triple prime, such kind of expression. It is just the denotion. This is for a catalytic reaction where it will be per gram of catalyst. Reaction rate per gram of catalyst.
Okay, ma'am.
Okay. So rewriting the expression, this is what is the final expression you get. Dx by dt is equal to minus Ra prime W into W by Ca naught into V naught. Now, how do you express the rate of the reaction? What is the rate of reaction? How do you find the rate expression? They have given some A gives B. So they have not given any information on order of reaction or anything, right?
Um,
Have they given?
No, ma'am. First order.
How do you assume it is first order? If at all you're saying first order. There is something given in the question from which you can decipher what will be the rate expression.
I mean, it was given that it's independent on concentrations A and B. It will be zero order then.
Is it for the reaction they have given, or is it for the activity of the catalyst? Just look into the question again. The catalyst deactivation follows a first order decay independent of concentration of A and B. It is not for the reaction. It is for the catalyst decay expression which is independent of concentrations, because there are cases where this catalyst decay expression dA by dt will be a function of concentration of A and B. Say for example, it can be a function of both concentration of A and B. So the expression can be dA by dt is equal to Kd into A into concentration of concentration of reactant A into concentration of reactant B. That, in that way also, the decay can happen, right? Say for example, in case of catalyst poisoning, right, because of the concentration of uh, say for example, in the previous case, if it is going to be a catalyst poisoning with respect to water, then this catalyst decay will be probably a function of concentration of water, right? That is what this term means. It does not mean that the reaction rate is independent of concentration of A and B. Okay. Okay, hope you got it. So how do you find the order of this reaction is that they have given two indications. One is, they have given an indication that it is an elementary irreversible reaction. That means generally in CRE 1 you would have come across this. If it is an elementary reaction, then your order is same as your stoichiometric coefficient, right?
Yes, ma'am.
That means here in this case the stoichiometric coefficient for A is 1.
So the
And
order is
also it is an irreversible reaction, so it is going to be only a function of concentration of A only, which is raised to power 1. It is nothing but a first order reaction, first order irreversible reaction. Okay, you have to look into these terminologies. So especially when you're uh, uh, writing some competitive exam like gate, they might not give, then you shouldn't end up oh, they didn't give what is the order of the reaction, so should I assume or not? See, you may again in there you're not deriving the entire expression, but you're just going to make the answer. But sometimes they will ask what will be the expression for the rate of reaction, right? So that case also, you have to look into these each and every term. So this elementary reaction is nothing but where the order will be same as your stoichiometric coefficient. So these are small informations that you have to look into. Okay.
okay, ma'am.
Yeah. So with that, what happens? Your rate of reaction is going to be a function of concentration of A raised to power 1. But here again, since there is some catalyst deactivation process that is also happening, so your rate expression will have a term of activity of the catalyst also. So your rate expression will be minus RA prime is equal to K1 into A of T into concentration of A. Okay, now you have to substitute this expression into the performance equation, and then you will get an expression dx by dt is equal to K1 into A of T concentration of A into weight of catalyst divided by initial concentration of A into volume of the reactor, right? And then further what you have to do is that we have to incorporate the expression of activity of the catalyst. So we got the expression as an exponential decay expression. That is what we have incorporated here, exponential of minus kd into t. Okay, and your Ca by Ca naught is nothing but your 1 minus x, right? You are able
Yes.
to follow?
Yeah, ma'am.
Yeah. And then substituting that, and then what you have to do is that you have to rearrange the terms and integrate the expression. You will get an expression like this: ln of 1 minus x is equal to k1 into w by kd into v naught into 1 minus exponential of minus kd t. Okay, this is nothing but just your integrations, right? Mathematics.
Yeah, ma'am.
Yeah. And finally, if you rearrange these terms, you will get expression, you will get an expression for the conversion. So your conversion is nothing but 1 minus exponential of minus k1 into w by kd into v naught, where k1 is your reaction rate constant and kd is your decay constant for your catalyst decay constant, into 1 minus exponential of minus kdt. Okay, this is going to be your final expression. Fine. You're able to understand, right?
Yes, ma'am.
Yeah, fine. That's it with the presentation. And that's it with the session. So, do you have any other doubts?
No, ma'am.
Okay. You're clear about what was all explained in the questions, right?
Yeah, ma'am. When it
Yes.
will be shared in the forum, ma'am?
Yeah. I mean, it will be, you will get the link in the course page. You will be getting the link in the course page. I think the NPTEL team will be sharing you the entire video and also the presentation file. Okay.
Okay, ma'am.
Yeah. Just go through it. And in case of any doubts, uh, please upload in the forum your questions so that it will get answered. Okay. Also, in the next session, also you can ask those questions. Fine.
Okay, ma'am.
Yeah. Fine. That's it with the session. Okay.
Okay, ma'am.
Thank you. Let's meet in the next week. Hope you are able to solve the assignment 3, in a better way. Right. Also, please go through the lectures. Please go through the lectures and also go through the lectures. Try to go through the lectures before the live session so that you
Yeah,
are
ma'am.
able to answer the questions. Okay.
Okay, ma'am.
Okay. Fine. Yeah. Thank you. Then.
Okay, ma'am. Bye, ma'am.
Bye.